Here's a problem from 1996 under the category Arithmetic with Literal Equations. Given the following map, how many different ways are there of traveling from A to B if a person never travels west or south? So this problem is not the typical problem that you would see under the category Arithmetic with Literal Equations, but it's a good problem to do because it has some nice solutions. So the problem says that you can only move this way or that way. So for example, a path that looks like this is not allowed because here you're going down. So there's two ways to do this, and first let's look at the way where you've categorized the lattice by the number of ways to get to each point. So looking at the big grid that I enlarged, the way of getting to this point is one. There's only one way to get to that point, and there's only one way to get to this point. Also, there's only one way to get to each of these points, since you can't move down. So you can't go like that to get to that point. Okay, but what about a point like this? How many ways are there to get to that? Well, intuitively, we can see that there's two ways. And that makes sense because the number of ways to get to this point is 1, and the number of ways to get to this point is 1. So if you add those, you get 2, because to get to this point, you have to pass through either of these. And same thing here. There's 3 ways to get to this point because either you come from this point, and there's 2 ways to come from this point, or you come from this point, and there's only 1 way to come from that point. So you add them. And let's fill in the rest of the grid this way, where you add the 2 adjacent numbers. And you can see as the grid gets more complicated, some of this stuff you can't see by yourself. Like it would take a lot of time finding these combinations. So this method makes it really easy. And see, there's 20 ways to get to point B, so the answer is 20. Now here's a second way to do that, this problem. So let's erase this grid. Let's consider this path. And let's write it as up, right, right, up, right, up. So that means first you go up, then you go right, then you go right, and then you go up, and then you go right, and then you go up. And also, let's try a different path, like a simple one. In this path where you go up 3 times and right 3 times, you just write it as up, 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 right, right, right. And you see in all of these paths, there are 3 ups and 3 rights, because the grid is to go from A to B, you have to go over 3 and up 3. So in all cases, there's 3 U's and 3 R's. But each path has a different sequence of R's and U's. So let's see what this sequence that I just wrote is. So that would be right, up, right, up, right, up. So as long as you write 3 R's and 3 U's in whatever order, you can make a path. And this is important because we need to find the number of ways that the R's and U's can be arranged if there's 3 of each. So if there's 3 of each, you know there's 6 slots to put the R's and U's, but in only 3 of them there will be U's. Like maybe there's a U here, a U here, and a U there, and then the rest have to be R's. So the number of ways to place the U's is 6 choose 3. And if you don't know what choose is, you should check out one of my other videos on the binomial theorem and what n choose m is. So 6 choose 3 gives you the number of ways to choose 6 spots to put the U's in, and then the rest have to be filled by R's anyway. And this would be 6 times 5 times 4 over 2 times 3, and that's equal to 20. So that's the second way to do this problem, by seeing how many different sequences of letters that you can find, and each of those letters corresponds to its own path.